We know from Albert Einstein's work in the early 20th century that nothing in the universe can travel faster than the speed of light. It acts as an absolute cosmic speed limit for all matter and information. But deep within the mathematics of subatomic particles, Einstein noticed a glitch. The equations described a specific microscopic loophole where particles appeared to interact instantaneously, regardless of how far apart they were. He famously dismissed this anomaly as spooky action at a distance. To him, the math had to be incomplete, because any instantaneous reaction would break his absolute speed limit. Today, physicists call this documented phenomenon quantum entanglement. It occurs when two particles, like a pair of photons or electrons, become so deeply connected that they lose their individual identities and share a single unified state. The very existence of this phenomenon forces us to fundamentally rethink our basic understanding of how the universe operates. To see why this is so strange, let's look at how normal objects behave. Imagine two ordinary coins spinning in midair. They operate independently. If you reach out and stop one coin on heads, the other keeps spinning. What happens to one object has absolutely zero effect on the other. In the quantum world, entangled particles behave as a single physically fused system. Instead of flipping like coins, these particles possess a property called quantum spin, which is an intrinsic angular momentum that can be measured as pointing up or down. Before we measure them, both particles exist in a state called superposition. This means they are spinning in all possible directions, both up and down, at the exact same time. In quantum mechanics, observation is a physical intervention that forces a unified system to make a definitive choice. To test the limits of this connection, imagine taking these two entangled particles and separating them across the solar system. We keep one particle securely anchored in a lab here on Earth, and we send its entangled twin all the way to Mars. Even separated by roughly 140 million miles of empty space, the invisible link between them remains perfectly intact. As long as nobody looks at them, both particles continue spinning in that chaotic, shared state of superposition. This vast physical gap brings us right back to Einstein's problem. How does a single system coordinate its final state across millions of miles? The answer reveals itself the exact moment a scientist on Earth decides to measure their particle. The act of measurement collapses the superposition. The Earth particle instantly stops spinning and locks into a defined state, like spin up. In that fraction of a second, the particle on Mars instantaneously locks into the opposite state, spin down. There is zero time delay. It looks like the Earth particle sent a physical signal to Mars. But experiments prove that no message travels through the space between them. Because they are two parts of the exact same mathematical object, defining one half automatically defines the other by default. Entanglement follows the laws of physics because no communication actually travels through the space between the planets. Humanity is now moving from observing these quantum effects to actively engineering them. This is the foundation of quantum computing. This technology utilizes entangled, superpositioned particles to process massive, complex calculations simultaneously, eclipsing the power of classical computers. It also enables quantum cryptography. This is the creation of secure communication networks where the mere act of a hacker observing the entangled data instantly alters its state, alerting the user to the intrusion. The success of these systems confirms that entanglement is a physical reality we can reliably harness. Mastering this connection is the bedrock of these emerging technologies. Beyond the technology, entanglement challenges our understanding of the universe itself. If distance has absolutely no effect on how entangled particles share a state, then physical space might not be a fundamental property of our universe. The space we experience every day might simply be an illusion, a byproduct of the way quantum information is woven together beneath the surface of reality. The deeper we look into the quantum realm, the more we realize that the distances separating the stars might simply be a byproduct of how information connects.